Welcome back. One last short video about vector functions. And the idea here is we have a curve that we're following along, and we're feeling we have some velocity, but as we're going through here, if you're a NASCAR racer and you're going through here and you turn along the curve this way and then you turn along the curve this way, you really have a velocity, but you're feeling the acceleration. You're feeling that acceleration as you go through. And so, can we understand what that acceleration feels like in terms of our Frenet frame, in terms of this TNB frame? So, how much of the acceleration is towards t, how much of it is towards n, and how much is it towards this binormal vector? All right. So, we're going to do, this is a good application of our derivative rules, and so let's take a look at this. So we'd like to learn about the acceleration, and so to do that, what we're going to do is we're going to write, we need to take the derivative of v of t. And so how can we write down this v of t? Well, v of t is the velocity of the function, the speed of the function, times the direction in which it's going. Right? This v of t is some velocity times this tangent vector, the unit tangent vector. So let's now take the derivative of v of t times t of t. So the derivative of v of t times t of t, we have to use the product rule for a function times a vector. To do that, you get the derivative of the velocity, the speed, times the t vector itself, plus the velocity times the derivative of the t vector. Now this derivative of the t vector we calculated last time, right? We found the derivative, where did we get this? We have the derivative of the tangent vector divided by the length of the tangent vector, of the derivative of the tangent vector divided by its length is equal to the normal vector. So we can rewrite this as an equation that says t prime of t is equal to the normal vector times the length of t prime of t. So this is a number, and this is a vector. All right, so what this is saying is that v times t primed is equal to v times length of t primed times n. Okay, so that kind of feels a little bit sketchy, but the thing is, the reason why we would do this is so that we could break down this acceleration into two pieces, one that's in the direction of t and one that's in the direction of n. Okay, which is telling us that any of the acceleration happens in the plane that has t in it and n in it. And so none of the acceleration is in the direction of the binormal vector. So what we can do is we can, if we want to break this down, what we're saying here is acceleration is something times t plus something times n. And so this acceleration towards the tangent direction is the rate of change of the speed, and the acceleration times the acceleration in the normal direction is equal to the curvature times speed squared. All right, so what that's saying is if you're going through a curve, there's that curvature, which is a fixed idea in that curve, but the faster you go, if you take your speed and you multiply it by a factor of 2, you're getting an acceleration of a factor of 4. that's going through it. All right, so if you go through and you go through all the little bits here, so how we want to solve for this a of t and a sub n as a functions of r of t, well, you can go through and write down some information to get the ideas of how you can look at v primed and k times v squared in terms of a quantity that's v dot a. So if we take v dot a, so if we take this acceleration and we dot it with v, then what we see is, so we can take v times t times this, so we get v primed times t dot t. And now that's a vector, 2 unit vectors in the same direction, so this value is equal to 1. And then if we look at vt dotted with kv squared n, well, then you get 2 vectors that are perpendicular to each other. And so this dot product is 0. Okay, so why is this helpful? Well, it's helpful because it's telling us that if we're looking for v primed, then v primed is going to be equal to v dot a divided by v. Right, so this is equal to v dot a. So v primed is equal to v dot a divided by v. And if you look at k times v squared, then this comes back to the formula that we had for the curvature, which looked like this, except that it had a cubed on the bottom. Right, and so when we multiply by v squared, that cubed goes away. And if the interesting thing here is that the acceleration in the tangent direction and the acceleration in the normal direction, these formulas look very nice and symmetric. This one has a dot product, and this one has a cross product in it. So let's do one example here. Let's say we want to find the tangential and the normal components of the acceleration for this function. So to do that, what we'll need to do is we'll need to find r primed, and we'll have to find r double primed. So r primed is equal, what happens when you take the derivative of this? We get 1, 2, 2t. And what's r double primed? It's what happens when you take the derivative of r primed. So you get 0, 0, 2. And so the length of r primed, square root of 1 squared plus 2 squared plus 2t squared. So the square root of 5 plus 4t squared. That's the length of this. And so let's write down our formulas. So the acceleration in the direction of the tangent is going to be the dot product of these two vectors. So 0 plus 0 plus 4t divided by the length of this, 5 plus 4t squared. And the acceleration in the normal direction is going to be the cross product divided by the same thing, 5 plus 4t squared. And then the cross product of r primed cross r double primed. So we have I, j, k, 1, 2, 2t, 0, 0, 2, I, j, 1, 2, 0, 0. If we do down, 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 minus up, 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 we see all we have here is 4i in this direction, and we have minus 2j in the other direction. And so the length of this vector is square root of 16 plus 4, so square root of 20. So that's the acceleration in the normal direction. All right, let's stop there. And when we continue, we'll be talking about functions of multiple variables. All right, see you later.